Okay, I think that I am up next with the fun game called Where in Psi is X. Um, Once upon a time, this was a game. It works, I think, pretty well when you can form teams or people to consult with, but that is hard to do when all of you are individual and around the globe. So I think that the only way we can really do this is to um, go through the questions and just have me narrating the answers. But any and all feel free to um, speak up or disagree or post questions in chat or whatever. Andy Jiang is monitoring the chat for questions this afternoon. Okay, this is the game as I have it. What we have are a bunch of questions, and the answer to every question is a file in the Cipher repository. So it is worth bringing. If you wish to try to search some of these out on your own, you may wish to bring up the Cipher repository. github.com/cipher/cipher. Okay, so whenever you're on here, if you don't know this trick, it is very useful. In this mode where you can see the folders, simply type the letter T, and this will come up with a file search of the whole repo. So when Andy asked that question in chat just now about why there are several J matrices, I went here and I typed JK, and the first thing it suggested was the header for the JK object. And so that's what I was reading while other people started actually answering his question. So this little T shortcut is very useful. Broadly speaking, this is the overall structure of the Cipher repository.
Hey, Lori, I have a question.
Yep.
So how do you type T in again? Like, is it Control T or?
No, simply lowercase letter T.
Okay, I got it.
Yeah. There are some modes that it won't work in, but as long as you're in this folder mode, you're good. So broadly speaking, all the tests are in the test folder. Each of these are an individual test, and then there's also a PyTest folder within test, and there are different files in there that are individual PyTest, Psi API tests. So tests is a big one. Samples is auto-generated. Media is where you find logos. This has to do with the build process. This is where all of the sync documentation lives. This is not really active to users. CMake is resources for the build process. C- is not really active for users. And Azure Pipelines controls our continuous integration. There's a Windows and a Linux file in there. But most of the time, what you'll be dealing with is the Cipher folder. Now, in here are top-level headers. It includes Cipher. Top-level non-compiled files like basis sets can share Cipher. A few individual files, and then in driver lives all the Python code, and in source lives all the C++ code. So dialing down into source a bit, anything with export, this is what links C++ and Python. So when Jet claimed that everything was hooked up libmints to Python, that happens in this file, export mints. And so you can see that, for instance, the basis set object, find a better choice. Okay, the matrix object, setting name on it, the number of column dimensions, and so forth are all outlined there. Going a bit further into the core, these are all the individual modules. So det.ci for full CI, df-awk that you heard from from Lure this morning, our fast df-mp2 code, and some of the libraries like libfock that handles a lot of SCF things, and libmints that Jet was just talking about. You'll notice that at this level, there are actually 3 Cipher in the path. This top one is the repository. This second one is the code, both Python and C++. The source is where you get into the C++ code. And then this is the top level that holds the modules. Okay, so that's the brief tour. And now we will try a few questions from the game. So, question number 1. This file, after configuration and installation, becomes bin Cipher, where bin Cipher is the thing that you execute. And it's almost impossible for me to gauge if you are actually trying to do this or how far you're going. So I will simply show you that from the top level, go into Cipher, that run Cipher is the file that we're speaking of. And this looks just like an ordinary Python file. It has these @ symbols, yes. And so these get substituted at build time, and then this gets installed into stage bin Cipher, and it's what you actually execute. It's doing, it's looking at all the arguments that you give it, the input file, the output file, the scratch directory, memory, and so forth. And essentially under the hood, this is importing Cipher and then running it as SciAPI. And so it's taking the DSL input file and turning it into a SciAPI input file. And indeed, I've got it right. Okay, next question. Where cross-module options like e-convergence are defined. Now, whenever you hear about options, the key file to go for, I'll keep going back to the top so you have a better notion of where things are. Cipher, source, read options. This is an exceedingly long file, starting 5,000 lines, and all of the options that you can pass to Cipher, except those that are defined by plugins, are defined here. And in particular, that question was asking about cross-module options. And so those are the ones that are valid for every module, or that every module is subject to. So you'll see if statements within this file that separate out the blocks of options for different modules, in this case for the optimizer opt-king. But way up at the top is a section of globals. And so it is here that e-convergence lives. Here we go. That e-convergence nominally defaults times 1 to the 10 to the minus 6, but this does get adjusted in the driver depending on the type of calculation. Once again, I got it right. Okay, organization. A tutorial test case with an open shell system. Now, these tutorial test cases are some that David mentioned in his basic runners tutorial the other day. We start at Cipher for test cases, go into tests, and then scrolling down, there's TU 1 through 6. Yes. And this CH2 energy looks like a likely one. And indeed, CH2 is a triplet and needs UHF. So question 4, where molecule is defined. Now, whenever you think of something being defined, if it's an object, as a C++ object, then what you're going to want is a header. All headers in Cipher are .h. All C++ files are .cc, just for the usual extensions. We don't do HPP or CPP extensions. So we'll start back up at the top, and this is a good place to try out the T search function. So molecule.h would be a good guess. And here is where you have to avoid clicking on the geometry molecule and instead click on the Leibniz molecule. Because if it's fundamental to psi, it's probably in Leibniz. And so this is where the class molecule is defined. And you see this little psi API. So PyBind11, when it builds this all into a library that Python can import, it hides all the symbols from the C++ layer so that you only get them from the Python layer. And this is very useful for PyBind11 because it results in a smaller executable and reduces the potential for namespace conflicts. However, Cipher has the C++ plugins that Jet just demonstrated. And so those plugins do need to be able to see those symbols. So this little psi API means that this is going to turn into a class that is visible to a plugin. So I got it right, Leibniz molecule.h. Question 5, where the orbital basis 631 G star star is defined. First of all, we need to know where basis sets are, and from my early introduction, you might guess that they're in share. And the other thing you might see is that star star looks like a rather dangerous name for a file name. And the way Psi handles this is certain things, if they start with, if they're stars, turn into S's. If they're parentheses, they turn into underscores. If they're pluses, they turn into P's. So I will again try my full search function here, 631G, and that SS means that G star star is the likely file. And it is indeed in the share folder. GSS. And Psi uses Gaussian basis set format. The only difference from Gaussian basis set format, unless you're getting into really high angular momenta, is that the first line we have Cartesian or spherical. That indicates the 5D or 6D as the developer of the basis intended. You as a user can always override this, but this way we get the default right. Okay, question number 6, where the Hartree-Fock class derived from wave function is defined in C++. Okay. Once again, I am going to guess that this is Hartree-Fock.h, and this is all in libscf solver. So we're looking for a class Hartree-Fock that is derived from wave function. And this is just what we promised. Now looking at the libscf solver folder, notice that there's an HF and an HFCC. And then there are further classes that are derived from those for restricted open shell, and unrestricted. Indeed, libscf solver hf.h. Okay, classes, where the Hartree-Fock class derived from wave function is exported to Python. Okay, so we just found the C++ class, and now we need to find where it gets exported to Python. Now, you remember that a lot of the things that are exported to Python are in files that start with export. So I will try searching for that. And then we saw that Hartree-Fock was derived from wave function. So I'll give it a guess that it's export wave function.
Lori, I'd like to bring up an interesting point that Zach brought up.
Okay.
Zach said that Jet's demo had him thinking about the process of lineage triplet. And he says it always multiplies matrices in order A times B times C. Or it does AB first and then C. He asks, shouldn't we be checking the dimensions and do A, B, C when it results in less overall work where B, C is performed first?
I do not know.
Okay, I just think it's a good point he brought up.
Yeah. Okay, so here's our SCF Hartree-Fock class, and it's turning into a Pi class. If you're ever dealing with these export functions, one thing that's important to realize is that from here to here is actually one line. There's exactly one semicolon at the very end, and all of these are just tied together by dot for each of these other individual associations that you make. And so, for example, the set energies Python function on the Hartree-Fock class, that's the first argument here. Then that gets associated with this C++ function. And I'll show you this one, the CP-SCF perturbation. So name of the Python function, name of the C++ function, a doc string, and then name underscore A, function underscore A lets you use key name variables. You must have exactly one semicolon at the end and none in the middle, or you'll get some very strange compile errors. So indeed, export underscore wave function. Okay. Where module-specific options like DFT dispersion parameters are defined. Okay. I cheated on that one because I suspected that the answer had changed since I wrote this 2 years ago. But indeed, any options other than plugin will simply be in read options. Okay. Question, where can you get geometries for the S22 database? By now, just about anywhere in the world. You see archive, end of a good number of papers, but the Cipher specific answer is, we'll try to search S22, and indeed there is a directory of databases that have Cipher molecules for a lot of well-known databases. They're forming a molecule, and this is the geometry. And these often have these often have the literature reference values also stored up for convenience. S22.py. Okay, historical question. Where Cipher defines its C-friendly level 3 BLOS. This is historical because you are not going to be able to predict where on earth this is from the name of any file. And in fact, to go into source and start looking at all the modules, and these library ones are good candidates. And the one we want, in fact, is this libqt, where Qt is the quantum trio, which back in the day at UGA was Daniel Crawford, David Sherrill, and Justin Furman. Kept wanting to say Turney, but that is quite wrong. Okay, and so these BLOS are the likely ones. This looks like BLOS 1. Let's see if there's a BLOS 3. No. Not there either. So I will. Okay. When no library looks relevant, always check libqt. That's where a bunch of the staples that went into Cipher or went into Cy3 and have endured for their usefulness do live. Okay, and BLOS int fc23.cc. I think I will go on answering these until, I think I started at 2:40. So I'll answer these until 2:10 and then we'll stop there so that you're not too bored. Okay, driver. How Cipher knows to run det.ci when you enter energy FCI. Okay, so back to Cipher. Go to the Cipher code. Then driver is where all the Python lives. And in here, proc routing is where all the call this C++, then call that C++, then call that C++ instructions live. And in particular in here, there is a proc table. And this is if you make a call to energy in MP2, then it calls this Python function. If you make a call to gradient and LCCD, it calls this Python function, and so forth for Hessian and properties. So in this case, for full CI, it is going to call run.ci. Run.ci is in a function in another file. Proc routing, proc table. Okay, how Cipher knows to run CC energy, then CC density modules for CCSD dipole. So a dipole sounds like a property, and all of these are going to run CC property. And back to proc routing, all of the commands that those functions in proc table call are in proc.py. And so this is another very long file, but we will look for that function that we just know got called. And so here is, after a bunch of logic, because properties in couple cluster are complicated, Aha, here we are. We are calling these. Okay, I've lost where it starts, but call CCH bar. As needed, call CCEOM, call CC lambda, call CC density, call CC response. There's about 7 of these that form the whole CC suite. And so this is where the actual C++ calls, you determine what order those C++ modules are run in. Proc routing, proc.py. Another driver question. Where direct from libxc v3lib is defined. Okay. So back to proc routing. DFT seems a likely folder. We'll try super functional. Nope. Oh, libxc functionals. Makes sense. Okay, and there we have b3lib mapping to this key code, which is part of libxc. So libxc underscore functionals.py. That name has changed a bit, but I think we found it. Okay, where a self-assembled hybrid functional like a mega PBE is defined, because we don't want to confine ourselves to only functionals that are available from libxc. So that's where all these underscore functionals come in. Okay, so here we can append to the functionals list parts that are defined in libxc, and then any additional parameters that we want to tweak the function with, the functional with, the hybrid funcs. Okay, in Python mode, turns your input file into Python. So back to driver. And then there's one file in this that it isn't actually hooked up to the driver. It's sort of standalone, and that is the input parser. And this is what does a lot of regexes and identifies your curly bracket blocks and other elements of the Python language, and forms regular Python API calls from them. And so your Python comes into this, and PyAPI comes out of this. And then the PyAPI is what gets executed. Input parser.py. Organization. Where to reserve a SciIO file number, like 180 for orbitals. Okay. Back to top level Sci and code. So this sounds like something that is very broad to all of Sci. So we'll try the includes. And indeed in scifiles.h is what associates this string to this number so that you can use either one and reserve a particular scratch file number for your module. The sci-files.h. In Python mode, file that imports Cipher behind the scenes, so you can pretend Cipher is an executable. I think that this is that run Cipher that we looked at in the first place. Yes. So the answer to this one is the same as the first question. Okay, multi-language, where SCF iterates nowadays. So a little while ago, we underwent the process of moving the SCF iterations from C++ side to Python side, so that we'd have greater control and chance to interject code. So, like all connection and between Python and C++, a lot of that is in proc routing. And here, there is an SCF proc procedure, and happily an SCF iterator.py. And so this is actually an extension to the C++ class in Python. Sorry, the C++ classes in C++. These are Python extensions to it. And then this is that SCF iterate function that is actually going through all the iterations. SCF iterator. Okay, so that's been half an hour. So to avoid completely boring you to tears, I think I will stop there.